everyone. I thank Gluon for giving me this opportunity. So today I will be talking about what I have done in last 3 months in Canada. So my study was about pseudo-gap phase in electron probe tube plates. So this heading is something I don't like, but because it's too complex and to understand in first glance. But basically pseudo-gap phase is like you see some special structure of electrons density in momentum space, and which is very anti-intuitive. So we want to study that structure, hence this study has been conducted. Okay, so first my project was in material science, that is I want to study a material or a special material. To do that I need to choose my materials, right? So first first material I chose is superconductors, because superconductors are cool, right? And then what this graph is representing is on the y-axis I have superconducting transition temperature. That is, there is a metal or a material, they become superconducting at temperature Tc. And here I have year of discovery. So this is like progress of discovery of superconductors over the years. So if you see here, there are some room temperature superconductors as well, but there is one small problem with it. The pressure has to be near to the Earth center, so which cannot be maintained in laboratory. So what we do is we trade off the pressure with halfway. So we study with materials which are halfway there, that is around 150 Kelvin, whose transient temperature is 150 Kelvin, and we choose these materials to study and perform theoretical experiments or practical experiments. So to study a lattice or a material, we need to solve, basically the idea is to solve Schrodinger equation. To solve the Schrodinger equation on the lattice, we need a Hamiltonian or something with which we can calculate the energy, because energy of the sides or energy distribution in the lattice gives the whole information about it. Okay? So we start with something known as the Hubbard model. Okay? So I'll first explain what is the model or what are the terms, and then I'll say what these things actually mean to us. First, this guy, first term, it is a whole quantum mechanics jargon, but basically this accounts to the energy of the electron when it jumps between lattice sides. That is, there is a periodic lattice, and this T, the constant, represents how much energy it requires to go from lattice side I to lattice side I plus 1. And here we have, this is known as the Hubbard repulsion term or on-site repulsion term. And here if you see, the site index is the same, but the spin index is different. Okay? So this guy accounts to the energy of the electron to stay on one side. Okay? What affects that energy? One, the foremost principle which affects that energy is the Pauli exclusion principle. It states that two electrons with same spin cannot stay on the same lattice side. So here if we see, there is a expectation of n spin up and n spin down, and if these two are plus 1, which means both are same spin, this will be a plus u contribution to the Hamiltonian on energy. So which is bad, because always system tries to go to the lowest energy state, and this addition of energy is bad for the system. And if this is opposite spin, it is good. So this kind of includes Pauli exclusion principle, but not exactly. Like there will be atoms, or in your model, there will be sites where you have both spin up and spin up. This doesn't prohibit it, but it kind of prohibits it. Okay. So before moving further, in the next slide I will show the model we use. There is some quantity I want to show you guys, which is known as the spin susceptibility, or it is just a correlation function. So this can be a spin or charge susceptibility. What these terms are is, 1, 2 means lattice side 1, lattice side 2, and here is spin on the lattice. So if my spin on the lattice are correlated, or if I have two lattice sides, if the spin is same, this correlation function, what happens, it turns out to be some positive number. Okay, if they are not correlated, that is, if the spins are the average of products and product of averages is equal, then my correlation function turns out to be 0. That is, the spins are not correlated. Okay, this is one quantity I want to introduce, because we calculate this quantity or use this quantity in the model. Right. Now we jump directly into the two-particle self-consistent method or TPSC. Yes?
The last slide, the N you mentioned, that is the same N you mentioned in the Hubbard model, right? It's the same N, right?
Here N is the electron density, or N is the, suppose, spin at lattice site 1.
Yeah.
Okay? And this is N prime, sigma prime, that is spin at lattice site 2.
That is the same N then you used in the Hubbard model, right? On-site repulsion that mentioned. Last one. Yeah.
So
Yeah.
here, yes, you can say that. But we have to calculate these guys. But anyways, we'll move on. These are just expectation of spins. That's fine. Okay. Now the model itself. First, we start the model with an ansatz. So this is a semi-analytical approach. It is not something like DMFT or other models where you solve everything computationally. First, you start with some very sensible ansatz, right? So first ansatz we have to solve a differential equation. So what we do, we make an ansatz based on Pauli exclusion principle. Okay, that the solution will satisfy Pauli exclusion principle. With that ansatz, when we calculate the self energy, or this guy, this is like the solution of the differential equation. When you do that, you get this as your solution. Okay, and if you look at this solution, one thing to notice is this is a Dirac delta function or a weighted Dirac delta function. So this solution is a good solution, but there is a problem, that is it is a weighted Dirac delta solution which cannot be a sensible solution of a function of a material. But this solution satisfies Pauli exclusion principle, which is much better than previous models. Next, what we do is with these guys, with these calculated, I can calculate a two-particle quantity. That is the correlation function basically. So I calculate it. That is the two-particle quantity. This guy. So here it becomes U spin, which is renormalized to look like this rather than U. Why I am mentioning U spin is that there is a precursor model of this, or a previous model, which is known as the RPA, which has the same steps, but there is some difference in the steps, and that model does not satisfy Pauli exclusion principle. So I'll show you why I wrote U spin. But anyways, then we have this two-particle quantity. So this two-particle quantity, what is the significance of this is, this guy is a Dirac delta function. This guy is just one particle quantity. If there are resonances between two electrons, this guy cannot see that, because this is just a Dirac delta function. My function is like this. It is not sensitive to resonances or collective ones. But this guy, it is a two-particle quantity. It involves two wave functions. So resonance between these two wave functions can be recognized with this quantity. So the next step is that we use this quantity to again find a solution, the same solution, which is sensitive to collective ones, which looks like this. My self energy, this looks very complex, you don't have to worry about it, but one thing you have to notice is that this is no more a Dirac delta function. This is a nice function which is sensitive to resonances, because it has information about two particles, right? These U, chi CH and chi SP, these are two particle quantities. So we are done with the theory. So now advantages. What are the advantages of the theory? It is a non-perturbative theory. Right? For now, all the theories to deal with correlated electrons are perturbative. What do I mean by perturbative? We start with the exactly solvable Hamiltonian. We add a small term or some term with a small parameter. We vary the parameter and find the solution. Right? But this is not that. We start with a sensible ansatz which satisfies exact results. And then it again satisfies many results, including Pauli exclusion principle and Merwin-Wagner's theorem. But Merwin-Wagner's theorem is that there are no phase transitions possible in one dimension and also in two dimensions. Yes, and that can be seen with this theory. If you simulate a material in one dimension or two dimension, you can see no phase transition. And the validity of this method can be easily checked. This is one of my favorite points, because to check if the method is working or not, I can calculate two things, that is one particle quantity and two particle quantity, and I can compare these two to check if my method is okay. So it has its own internal accuracy checks, which is something very nice I saw in this method. And the last thing, this is the most thing I like, is that I can run the code on laptop. Generally, the codes for correlated electrons cannot be run on laptop, they run on clusters or very big computers. But this, as it's a semi-analytical method, all I have to do is make a momentum grid and apply the function I got, and that's all. And so there are some disadvantages as well. It does not work in one dimension due to the answers we made, and also in the answers we made, we did something which will also not allow it to work in strong coupling region. What do I mean by strong coupling region? So initially when I was talking about the Hubbard model, I showed T and U, right? So T is the hopping term, right? This guy corresponds to the movement of electrons or the kinetic energy of electrons, and this guy corresponds to the potential energy of electrons or energy on staying on one lattice side. So we always talk about coupling of the electrons or the correlated nature of the electrons based on the ratio of U to T. That is, if my energy of electrons is lowest when it stays on one lattice side, it will stay there, it won't move. If my energy of lattice is very high to stay on the lattice side, it will try to move. So how does one decide that? Based on the ratio of U to T. Based on these parameters, based on these parameters it is measured. And when I say strong coupling, it means that these two values are comparable. That is, U and T both are happening. There are weak coupling regions where I can ignore this term and I can only take this Hamiltonian. This is known as the tight binding Hamiltonian, where electrons are bound to a lattice side. And then I can work with this. Or I can just work with this for a case where my electrons won't move. But the problem comes when we have the comparable values. For that, we make all these models and all the theory to predict or see what correlated electrons does in a material. And yes. So now, that's why there is no Mott transition. Mott transition is like another correlated electron state. 2 minutes left. Okay, correlated electron state where electrons are almost frozen due to the ratio between U and T. But anyway, it doesn't work in that region because it's a very strong coupling. The model only works for weak to intermediate coupling.
So Mott transition mean here metal insulator transition you were mentioning, right? As you were mentioning the Hubbard model.
Yes. But it does not work in that region, negative U. Anyway, so I will compare this method with two other models. One is the random phase approximation and the other one is the quantum Monte Carlo. The random phase approximation is the precursor set because if you see the equation of the susceptibility calculated, it is almost same, but there is just one difference that I have here. U is renormalized, and this is better because when I calculate U in my model which satisfies Pauli's principle, the U I get is 2, suppose here, and here the U I have in RPA is 4. So that is why this TPSC is much better than RPA. And also this graph I made, and this graph was made in 1994 when the theory was first proposed. And this is a comparison of the model with quantum Monte Carlo model. What does quantum Monte Carlo? What they do is, any differential equation you can solve it by numerical integration. Just put everything together, put what you want together and integrate on both sides. Right? And you can integrate using quantum Monte Carlo methods or Monte Carlo methods. What Monte Carlo does is, instead of summing up the area by dividing into rectangles, it will randomly sample points and add up the area. Okay. So here you have something known as spin structure. That is, it is the sum of dot product of spins of I and j. So if my spins are aligned together, my spin structure value will be more because it's a dot product between spins. If the values are not aligned or the spins are not aligned, it will be less. So it is just a sense to give you what this means. The solid line is the TPSC and the dotted lines are quantum Monte Carlo. And quantum Monte Carlo is accurate up to statistical limit. So this working of this model is quite spectacular because they match very nicely. Okay, so now coming to results. First, this is the Fermi liquid plot. What do I mean by this? Whenever you have a normal metal or a normal material and you cool down the material, what happens? The electrons, they form a sphere around a lattice. So this is that sphere. This is that sphere in the momentum space. So just to say that this gives same results, I've made this plot. Then what are we looking at? Like I told about pseudo-gap phase, right? So this is the phase diagram of the correlated materials. And what do I mean by correlated? The ratio of U to T is comparable. That is what I mean correlated. And this is temperature and doping. Doping is like electron density or extra electron density. And what I am studying is this pseudo-gap phase to transition to a superconducting phase. This is what I wanted to study, but the calculation for the superconducting transition is too high. The computation is high, and I'm still running calculations. So I'm just presenting pseudo-gap phase. And what makes pseudo-gap phase interesting is that this is the Fermi surface, or this is the distribution of electrons in the momentum space at low temperatures, which is quite anti-intuitive. Right? Who will expect electrons to be distributed among lattice sites like this? So this is why it's interesting. And this is my plot on the left, and this is an experimental plot made by angle resolved spectroscopic, angle resolved spectroscopy, or RPS results in 2002. So this match is quite spectacular because with the results, with the experiments as well. And some more plots. This is also a pseudo-gap phase. What do we mean by pseudo-gap is that here if we look at, there is a dip in the Fermi surface. That dip is not completely to zero, but it goes to some height. So it's not completely a gap, it's a pseudo-gap. That's what we mean by pseudo-gap phase. And what can we do in future with this? That is, in graphene-based materials, they form a highly correlated state in some materials, like twisted bilayer graphene at magic end. So we can study this type of correlated materials or correlated states in graphene, which I will do in my BS project. And yeah, that's all for the talk. I'm thanking Mitax for the opportunity. And this is the Institute Quantic where I work, this building. It was I can say for sure this is the fanciest building I've ever been in. So this is a big board, and here all the presentations happen. I had my office somewhere here. It was quite nice. This is all our group. This is my professor, and she was my PhD advisor, and here I am. Almost not visible, but it's a very big group. It consists of 2 professors. And here in the background you can see Abhishek Kumar. He is a pass out from IISER Kolkata around 2006 or somewhere. He did his PhD in the University of Colorado under Dimitri, and now he's done with his postdoc there, and now he's again moving back to America for some other postdoc. Yeah, thank you very much for your time. Any questions at all, just ask me or ask me personally, I can answer.